Okay, so today the general topic will be quantum groups. But to introduce this, we need a lot of preliminary information. We need to know something about B-algebras and Hopf algebras, before we can introduce quantum groups. Now, so our starting point is associative algebra. Associative algebra, U. I'll write over F, but in fact most of the time F will be the complex numbers. It may be also R, but most of the time it will be the complex numbers. So that's an associative algebra with unity. So I write this because it's an element of the algebra. It's not the number one, it is the element of the algebra. And such an algebra is called B-algebra. U is called U bi-algebra. Now, if it's an algebra, of course, it has a product, and of course you can add elements and multiply by numbers. Of course, this you know. So in fact, of course, you have also a zero element and unit element. Now, it's a B-algebra. There is two additional algebra homomorphisms, which are called commultiplication or we should say also coproduct, for short, coproduct. Like here we say multiplication and we say product. So we denote this by I denote this by delta, small delta, although sometimes in literature it's called big delta. Because I'm using in my lectures the big delta for other purposes. So this is so delta is a map from the algebra into the tensor product of the algebra. Now I hope that you have passed linear algebra and know what's a tensor product, because otherwise we cannot progress. And so to each element there is such an element. So in fact, what it means is that if x belongs to the algebra U, then delta of x would be representative like a sum x1i tensor x2i sum over I. It's a finite sum. So this is what it means, that you have some elements, and all of these, they belong to the algebra itself. And there is one requirement on this coproduct. It is that if I take the element 1, if I take the unit element, then the result, it should be the tensor product of these two. The result is very simple. on both sides I take the same unit element. So this is a special requirement for in this case. So this is from the algebra to the tensor product, and this is from the algebra to the numbers. And okay, so it's clear what it means. That means that epsilon of x will just belong to f. It will be just a number. And then special requirement, again related to the unit, that epsilon of the unit element is the number 1. This is of course a convention, but this is, we have to make some to make some normalization. And there is a property, an axiom called, which both fulfill jointly. It's called an axiom of co-associativity. Remember that associativity was meaning that x point, y point, z is equal to x point, y point, z. And here the co-associativity means the following. If I take, so this is, now I'm taking, this is, I'm working from, I'm working now from this, works from, starting from U and going to the triple product, to the triple tensor product of U. And it is the following, the following thing, that if I apply first the map delta, which means that I'm going from here to here, and then I have, and then I apply delta once more times the identity. So I went first with this map with this map I went from U to U times U with this one, and then with this map I applied delta on the first element and identity on the second element. Identity is just identity. Identity of x means that the result is x.